Hello everyone. Today I'd like to introduce ln x is equal to the integral of 1 over x dx, derivation and use. So first of all, why should we care about the integral of 1 over x dx is equal to ln x? Well, for one reason is that this is at the very heart of the definition of entropy. And in the future, I'm going to be doing a presentation on entropy and its relationship to in thermodynamics and in Claude Shannon's communication theory and others. And I need to have an understanding so people can follow some of the arithmetic or mathematics involved. So the other reason is, like I was just hinting here, about that integral of 1 over x dx equals ln x plays a large role in the science of thermodynamics. And for example, Albert Einstein has over 20 patents. I was able to look them up, and I was surprised to find that roughly 80% of Albert Einstein's patents are for refrigerators. And so thermodynamics and refrigerators, once you understand that, it really, it's kind of, I find it funny, because it really does help to understand, one person understand general relativity. And interestingly, I have a little plus sign there. He actually had a patent on other things as well, and one of them was a patent for a new form of woman's blouse, which is, I found that a little surprising. Maybe not, though, if you know Einstein's character a little more deeply. Anyway, I'm curious about that one. The integral of 1 over x dx also plays a large role in communication theory, including the work of Claude Shannon and some of his theorems, which has use in biology and even David Sinclair at his lab in Harvard talks about how the Claude Shannon's theorems might play a role in allowing the reversal of aging through some of the principles that Claude Shannon elucidated. So, and that's coming back again, we're talking about the integral of 1 over x dx. So let's see, how are we going to go about this? In this video, we will first introduce the integral of dx over x by showing what it means graphically. Now, I always like to, if wherever possible, take the notation of mathematics and turn it into something graphical so that we can see what it is all at once. And a lot of the work that I do, play work that I do, and real work too, I do it when I'm asleep, when I'm lying in different various states of sleep, from light sleep to deeper sleep. And I find that if I convert everything into something visual, graphical, I can import it into my dream state and manipulate it so much more quickly and more easily. And it's easier to remember. So I'm going to do that here. Otherwise, I wouldn't be making this presentation. So secondly, show why the integral of dx over x is the same as ln x. So I'm going to make the integral expose what it is. And you'll probably, I found this very, very interesting. And I wasn't sure it would work. And when it did work so spectacularly, it made me very, very happy. I'm still happy about it. So lastly, we will then demonstrate how to use this integral and what the common pitfalls are and how to avoid them. Because if you don't know how to use it, the knowledge of the mathematics, it's not very helpful. Let's see now. Move this over a bit. There we go. So let's go. Let's look at graphically what this function ln x is equal to the integral of dx over x, and I'm doing it from, in this case, 1 to b, where in the chart here, where b is the number 20. So x, you can see, is on, it's the numbers on the horizontal axis, and 1 over x is the measurement of the vertical axis, how high up it is. And you notice that 1 over x, at x equals 1, 1 over 1 is equal to 1, and you look up in the side vertical axis, and you see that at the number 1 on x, 1 over x is equal to 1, just as we'd expect. Let's go over to the number 10. So at the number 10, 1 over x is 1 over 10, which is 0.1. And we look here, there it is, the number 10, there's the point, and you go all the way over, and it's half of 2, which is 1, just as we would expect. 1/10 of 10 is 1. So that is the function, the line, 1 over x. And the integral of 1 over x dx is the area. Because remember, integration it produces the area under a curve, at least on 2 dimensions. And you can go higher dimensions, get volumes and so forth. But here, it's clearly representing the area, which I've shown in yellow. And I've done it from integrating the curve from the x equals 1 up to x equals 20, okay, in this chart. And that's what you're looking at, okay? So that explains what this function of 1 over x dx with the integration, what that is, and the physical meaning of it, graphically explained. So let's go on here. So now we're going to show. Remember, I said what we're going to do, and we've done the first one, show what it means graphically. Now we want to show why the integral of dx over x is the same as ln x. Now I've played with it for quite a while, and for most of that time, I didn't see why it was the two were identical, like it's an identity. So recently I decided to make the integral explain itself. I wanted to see it directly that the two were the same. So I want to show here, because I had recently done, here I listed all the recent presentations that I have. I'm going to move it over so you can see this one here. And I'll have to probably move it back, but down near the bottom, you see I did a presentation at this link here, showing my red arrow, this one, the geometrical meaning of E and J. So I just finished that, and it's kind of, maybe it's a coincidence, or maybe it's more than a coincidence, but that proved to be extremely useful. So let's look at this thing. Okay. So what we want to do, what my plan was I look on I want to show you the thinking involved, because it's not only applicable for this one situation, but you can use this type of thinking to make other mathematical functions expose their true identity. So here we have ln of x is equal to dx over x with an integral of 1 to b. Now notice on the left hand side here, ln x, it's what is ln? It's a natural logarithm. If you take e to the x and you do ln x is like the anti-function of e to the x, and what it does is when you do ln of e to the x, what comes out is x. It releases the exponent x, okay? So that's right at the heart of ln x. So what I want to do, and here's the way to approach this. I've demanded that we put dx and x both in the same language of natural logarithms, ln, so that I'm forcing the function to talk in the same units, so to speak, on both sides of the equation so that it has to tell me visually why they're the same, okay? So I embarked on this, and we'll do that right here. We'll embark on this. So how can we express x in the general sense in terms of ln, the natural logarithm? And yes, right here I've written it, x, and it's the same x as here in the bottom here, is equal to e to the ln x, because e is the anti-function for ln x, and what it does when you do e to the ln x, it produces the exponent, and so we have is equal to x, okay? And then what about dx? Okay, well, if x is equal to e to the ln x, which it is, okay, and that's a general identity, then dx is going to be the derivative of e to the ln x. Now, one of the things we discovered back here in this derivation, the geometrical meaning of e and j at this particular link, is that when you take the derivative of an exponential, you get the exponential function back in unchanged and multiplied by the derivative of the exponent, okay, which in this case is ln x. So we have what x is in a general sense, and we have what in terms of ln x, and we have what dx, the derivative of x, is in a general sense in terms of ln x. So we're actually ready to substitute these results here back into the integral of 1 over x dx, right? We'll put it in terms of ln x, so that both sides of the equation are in the unit, so to speak, or in the language of logarithms. And then, hopefully, when we're done, it'll show us directly why the integral of 1 over x dx is equal to ln x. So let's see this. It's like it's an experiment. Okay, so here I've shown this part we've already seen, this top part, but this is new, the hence. Hence b over integral of b from 1 to b of dx over x. And here I make substitutions. X here goes in the bottom, and it's going to be ln x, e to the ln x. And there we see it right there, e to the ln x. And dx is equal to e to the ln x times d ln x. So that goes in the top, because dx is on the top here. So I put it in, e to the ln x, d ln x. Now, this is where a person deriving this starts to get very happy, because, look, on the top you have e to the ln x here, and on the bottom you have e to the ln x. Those cancel. They cancel out, and you end up with just 1 on the bottom. Now, if you have 10 on the top and 1 on the bottom, it's just the same as 10, so you don't even have to write it. So we have it here that e to ln x is equal to the integral of d ln x over 1. Now, generally speaking, if you have the derivative of something, and you integrate it, then you end up with that something because it's like doing the anti-function of a derivative when is an integral. So you get rid of the derivative and you just get the function back. But we're integrating from the point 1 to b. So anyone who knows anything about integration knows that that's ln b. In this case, the function at b minus the function at 1, in this case. I'm doing from 1 to b. So it's ln b minus ln 1. Now, ln 1, e to the 0 is equal to 1. We proved that in that last link that I showed you. E to the 0 is equal to 1. So ln of the 1 is 0. It produces 0, the exponent 0. And it's 0. So ln b minus ln 1 is just equal to ln b. Okay. So that's what we're talking about here. Ln x and is equal to the integral of dx over x. We've proven that right there. And it's obvious when you make that general substitution, which is using identities, but just put it in terms of ln x, you can see directly that this integral is equal to ln of b, okay, in this case. And more general case is going to be ln b minus ln of the initial starting point, which brings up some issues that we're going to talk about next or soon. Okay. Now, let's have a look again at what we wanted to do and see if we did it. So we were on 2, and show why the integral of dx over x is the same as ln x. We actually achieved that, and in such a way that it just jumps out at you. And we did it by ensuring that the function had the same language, which is natural logarithms on the left-hand side, and it had the same language being used in the right-hand side. So it makes it expose why it's the same. Okay. So let's look at something next here. We've done 2. So what's the last one? Last one is we will demonstrate how to use this integral, what the common pitfalls are, and how to avoid them. Because if you know a function but you don't know how to use it, then it's not very useful. So let's look at this here. So it turns out that if you try to do, here's one of the problems. We know how to use it from 1 to b, or 2 to b, or 3 to b. It's going to be ln b minus whatever the value is, 1, 2, or 3. And you know what? We showed that it was the area under the curve. Remember that yellow area? And depending on where you start and where you finish, you get a different area. So that's what this function does for us, the integral of dx over x. So what about the integral of dx over x where you start at 0 and go to b? And it turns out that ln of 0 is not defined. So that function causes an error. Okay, when you integrate from 0 to b, it's ln b minus ln of 0. Well, ln of 0 is not defined, so it produces like an error if you do it on your calculator, and it's just not achievable. So that's good to know. So you don't try to do that. Okay, but how you can get around this is you can't do the value at ln of 0, but you can use it. You can do ln of a value approaching 0, however closely you want to get. Okay. So I have here. I just wrote it down in my own kind of language. What is it? I said is approaches, right? We can do the integral of 1 over x dx from something very close to 0 to b. And we can approach as closely as we want to 0, as long as we don't actually go to 0, right? And that's what I'm meaning here. And the result is going to be ln b minus ln of that little increment away from 0, whatever that small number is, okay? And again, I want to do keep it graphical, right? And see, so I want to show what the behavior of that, this term here, how it behaves, this last term, ln of some small value as it approaches 0, right? So I actually graphed that here. I have here on the vertical, I have a range of values going from 0 up to 80. And this is a scientific notation, so it's 8 times 10 to the 1, right? Which is 8 times 10 is 80. And so that's this value here, this line. And then the next one down is 6 times 10 to the 1, 6 times 10 is 0. Okay, so I'm not trying to be complicated here. I'm trying to simplify it. And then on the bottom here we have, okay, let's get okay, I'm going to have to put this in the back so I can get on my handy dandy radar arrow, send to back. There we go, got my arrow. So on the bottom here axis, I'm plotting 10 to the minus x minus ln x, so this value here, 10 to the minus x ln x minus ln x. And what you see is that it goes up linearly for one, which is for some of us, a bit of a surprise. But you go all the way down as this number, 10 to the minus x, gets so small, okay? Then in this case, 10 to the minus 30. So that's a decimal point with 30 zeros. And very, very, very small number. The value goes, and notice I have minus ln x here because I want to show how to use this. The value goes up not even 80, it's like 70. So it does increase, it increases the value of the integral dx over x as zero, the starting point approaches zero more and more closely. It increases the value of that because it's a negative of a negative. And it allows you to compute it. So for an engineering purposes or other, you can get as close as you like. Just do not take it all the way to zero because it's not defined and you'll get an error. So let's see here. How have we done? I want to do a little review and see where we've been. What our goal was to introduce the integral of dx over x, showing what it means graphically. We did that. Remember the yellow area under the curve, okay? Then I wanted to show why the integral of dx over x is the same as ln x. And we did that by forcing the expression to have the same language, like in this case, natural logarithm, on both the left-hand side of the expression and make it do it also on the right-hand side. So it exposes why they're the same, okay? And we did that, and it actually worked very, very nicely. Okay, so we did that. And lastly, we wanted to demonstrate how to use this integral, what the common pitfalls are, and how to avoid them. So I showed that you can have from any number to another number as the range, and it's basically the curve 1 over x dx, 1 over x, and then you start somewhere in the curve and go and stop somewhere on the lower axis, the horizontal axis, and you get the area under that curve, right? And how to do that. But I also showed, and then lastly here, we'll demonstrate how to use this integral, what the common pitfalls are, which the one I wanted to talk about was you can't start from 0 and go to a value, area under the curve, because the value of ln of 0 is undefined and you get an error, okay? But you can go as close as you like. We did that. So with that, I think we've covered this expression. And the presentation as well, we've achieved the results. So with that, I just want to say thank you very much. I really, really enjoyed presenting this to you today, and I hope it helped you understand this. It's something you can carry with you, and I hope the graphical images stick in your mind. So maybe like me, some night you'll be dreaming about it, and like me, I hope doesn't turn out to be some kind of mathematical nightmare. May it be a pleasant experience. So with that, I'll let you go, and thank you very much again, and goodbye for now.